So now we're going to move a bit beyond the carboxylic acid derivatives. We're talking about carbonic acid derivatives. So note that this carbon has even more carbon-oxygen double bonds, or carbon-oxygen bonds. We have 4 total carbon-oxygen bonds here. We have 2 single bonds and 1 carbon-oxygen double bond. This is a higher oxidation state than a simple carboxylic acid derivative. And note that even though carbonic acid is a molecule, it can exist fleetingly, but if you were to ever make this in solution, it quickly decomposes to give carbon dioxide and water. So if you guys have ever done that volcano reaction where you add sodium bicarbonate to acetic acid and it all foams up, that's because you're evolving carbon dioxide along the way. So even though this is an unstable reagent, derivatives where you don't have 2 OHs, where either you're going to have a nitrogen and an oxygen, 2 nitrogens, or 2 oxygens end up being actually pretty useful both in polymer synthesis and for use as intermediates and reagents and some other protecting groups in organic synthesis. So along the way, we're going to have new functional groups. These are functional groups that you do need to know. You have carbamates. They're also known as urethanes, so you may have heard of polyurethane materials. That's what these are made out of. Isocyanates, you should know. You should know the general form of a urea. I guess it'd be down here as the general form. You should know what a carbonate looks like. And you should know phosgene. Phosgene ends up being one of our very useful reagents for making these systems. So I made a new slide that spreads out this same slide just to draw out the mechanisms a bit more. But we can generally visualize the reactions, I think, fairly easily. In the case of additions to isocyanates, we have a carbon-oxygen double bond and a carbon-nitrogen double bond. Both of these would be electrophilic, so we can definitely add nucleophiles to the central carbon atom. After proton transfers, we're going to end up doing a single addition to make carbamates. If you were to add an amine to this system, it will give you a urea. And then with these sort of molecules like phosgene, we see we have 2 very good leaving groups. Phosgene is a very reactive gas. You can put it into solutions as well, use it a bit more conveniently. But this is very toxic, very reactive, and has been used historically in chemical warfare and does not have the nicest history in that regard. But it's a very useful reagent because it allows us to introduce a single carbon atom building block to make things like ureas or carbonates. And as we'll see, you can also make isocyanates with them. In this case, we get a double addition product where we can substitute 2 amines or 2 alcohols to give these other types of functional groups. So looking a little bit more closely at how these reactions take place, we know that we have this very electrophilic isocyanate. So we can imagine having an alcohol add in directly to this isocyanate. You can have the lone pair reside on either the oxygen or the carbon. Formally, it doesn't matter because they're both in resonance structures with each other. And similar to most of the additions in this section, what we're mainly looking for is keeping track of all of the proton transfers and how things add. So in the initial addition, we'd still have a protonated oxygen. And then after proton transfers, you can imagine this hydrogen going to this nitrogen and giving us the final carbamate or urethane product. The same process would happen with an amine. Now we're going to have an even better nucleophile. This could be a primary amine or a secondary amine. And this will be able to add in just to show that we could put the negative charge on either of the atoms. These simply represent resonance structures. I will draw this out. And then more proton transfers will give you, in this case, potentially an unsymmetrical urea. So now we can probably imagine having similar types of reactions with things like phosgene. And we also have this added question: what happens if only one molar equivalent is added? This is fairly interesting. So if we imagine having phosgene react with an alcohol, this is going to proceed just like we've seen in the past with reactions of acid chlorides. Phosgene is even more reactive than your average acid chloride, as these chlorines are certainly electronegative, will take electron density away. We'll have chloride leave. Keep track of my formal charges. We make a single intermediate. This is actually called a chloroformate. Chloroformate. You don't necessarily need to know that, but you can do a single addition with this. And the main question is, why can you do a single addition on something like phosgene, but it's harder to do single additions with other reagents? That's because this new intermediate is actually going to be less reactive than phosgene, because now we see we have this new oxygen that has a resonance isomer. Let me clear this up a bit. It has a resonance isomer that will stabilize the chloroformate. And we can imagine still another addition of alcohol with proton transfers. So I'll just draw two arrows to give us some sort of symmetrical carbonate. If you added a single equivalent first, you'd get mostly a chloroformate. Then you could add a second alcohol next if you wanted to make something unsymmetrical. The case of ureas, of adding amines into phosgene, is actually a little bit more interesting with one equivalent. So here we're going to have uramine react with phosgene. It'll go through the same arrows. So I'm going to draw two arrows to represent the proton transfers. But in this case, since this nitrogen lone pair actually, is a fairly good donor, this is able to directly kick out the chloride. And this intermolecular process happens faster than a second addition would. And so with one equivalent, you can make an isocyanate. Of course, if you had a second equivalent, amines are able to react as we saw before with isocyanates. And that'll give us a symmetrical urea. So in this case, if one molar equivalent is added, we can actually control a single or double addition. With one equivalent of alcohol, we don't have a hydrogen to deprotonate on the oxygen, so it stays as a chloroformate, as we see here. Whereas with a primary amine, we have a hydrogen that can be deprotonated, so it'll eject the chloride and go directly to an isocyanate. So this is a new way to make isocyanates. We're going to learn one more in the next lecture, which is one of my favorite reactions, but you don't get to learn that today.